Hi, it's me Noor Fatma Mansoor, and today in this lesson 3 we are gonna discuss about those previous topics with in detail. So don't skip this lesson, we're gonna do a lot ahead. So let's get started with this video. Today I just wanted to start by revisiting the previous topics to fill out the details. So these are the highlights of today's video. This is the objective of today's video, and these are the outlines. So first we will be covering in detail what is stemming and lemmatization, then about factorization in detail, matrix decomposition in detail, the essence of linear algebra in detail, then we will be visualizing SVD in detail, and full versus reduced SVD. So let's get started to learn about these things in detail. So yeah, in this notebook I want to wrap up some loose ends from the last time. So as we talked about in lesson 1 about the debate within computational linguistics, and I linked to a blog post by Peter Norvig, Google's head of research, who was disagreeing with Noam Chomsky, the father of linguistics, and he referred to a paper by Leo Bryan called The Two Cultures. Here as you can see, so modeling the it was about modeling the underlying mechanism of phenomena, and versus using machine learning ML to predict outputs without necessarily understanding the mechanism that creates them. So I wanted to show this diagram from it. Researcher had a long time ago looking at this process that happens within the one carbon cell metabolism, and here the rectangles, as you can see, the rectangles are representing some strains. The ovals represent for enzymes, and then we have all of these different kind of reactions. School of research was building computer models that have a bunch of PDEs showing how that these reactions happen, and then to give one example. So as an example here from the paper, this could be the velocity of for one, one reaction is kind of like of this complicated equation, but in the end we are just trying to see if we could replicate some clinical results in children with autism and Down syndrome. And so this is what we think the underlying mechanism is, to see if we can match these outputs. So it is like if we can recreate that kind of final output without necessarily having the mechanism. Okay, so the next thing is stemming versus lemmatization that I want to show you about. So stemming was pretty much like getting the roots of words, and lemmatization is kind in a way of stemming, but not quite there. Lemmatization is fancier, like we had the quote right. Stemming is the poor man's lemmatization, and previously we did an example of organizing, organizer, and organize, and the stem of those were organ, which is a completely different kind of word. So the next question that can be generated is like, when do we use stemming and lemmatization versus not? So lemmatization is more computationally expensive than stemming, which is true. So stemming is quicker and easier. So when to not use them? So when our model can like handle more and more complexity better, like neural networks, so you probably like don't want to remove stop words or use stemming and lemmatization, because that's a kind of throwing away your information. So something I wish I could set up for last time is I wanted to talk about factorization. So factorization is analogous to matrix decomposition. I just wanted a reason to tell why it is something we do. So looking at this at a much simpler case, so here you can see, so which is multiplication. You can multiply these numbers. Here you can see them. Let me okay here. So 2 into 2 times 2 times 3 times 3 times 2 times 2 is 144. So you can think of this as decomposing integers in something else, or you could say factorization is the quite opposite of inverse of multiplication. So the benefit of doing this is 144 is itself not a prime number, but you find a way to represent it in through prime numbers, which is a really nice property. So matrix decomposition are a way of thinking, taking matrices apart, and it's the quite opposite way of matrix multiplication, or in some cases matrix addition. The reason we have some nice properties, so the above case that I told you this, so that 144 is not a prime number, but we have the nice property of being prime, and it's the same thing going on with matrix decomposition. So here you have the matrix on the left. Here you can see on the left of the people walking through a video, and you can and you want to identify what's the background and what are the people, and so the goal is to decompose it a kind of two different matrices. So this is in this case the matrix is here the background is said to be lower rank, and so the next thing is, what are the nice properties that SVD has? So it's orthonormal. You know what? So what does it mean to be orthonormal? So it means that the columns are orthogonal to each other and pairwise normalized. So that it means if you can take the dot product of two different columns, so you get 0. But if you get do with a single column itself, so it will be 1. So that's it. So matrix vector multiplication. So then the last thing I showed up with this example, that comes from a computer vision, not NLP, but having of having a bunch of pictures of faces. I think I didn't link to it, but it was the faces of different features, facial features. So we can go to this one. So this is actually matrix multiplication. You can actually change the values here, change it to 4, change it to 7, then we can multiply it and then take it step by step, which will be really easy for us to understand. See here, now it will show the result. So we can also change the size of our matrices here. So yeah, that's all about matrix multiplication. Oh, sorry, I linked to it, but I didn't know that it was linked here. So these are the facial features, a bunch of pictures which are decomposing them to their facial features. So one of these matrices would represent the different features. Here you can see the nose bridge here somewhere right on your eyebrows, I think. But it was just an example. So matrices as transformations. So these 3 blue 1 brown videos are really good. This video is from Essence of Linear Algebra series. Let me show you. Let me run this. So it will just appear here. It will just be appear here if you see. So here, so it will appear in some time. So it will take time if you have this notebook after the class in your computer. So it will take time to load. There, you get here. So it is a video from the Essence of Linear Algebra series. It gives a very visual and geometric perspective on linear algebra, and I think this video is great if you are a linear algebra beginner or you are feeling rusty about linear algebra. So if you're interested in kind of thinking about how it relates to SVD, and how I would definitely recommend looking at this video. I also included the code. Okay, let me show you. So I also included the code, like how we can transform the over data in CSV files. So here is the code for NMF SVD. You can see it's a pretty simple and straightforward, so you can look it after. So yeah, the other thing I wanted to discuss is advantages and disadvantages of SVD and NMF. So NMF are values with non-negative, as we know, non-negative matrix factorization. So these are non-negatives and can be more interpretable, and for SVD we could have negative values for the topic, so it will become more complex for us. So yeah, and then the other thing is randomized SVD offers a speed up. Okay, so this thing is like lying on SVD with a big matrix is really slow. So this is from a PyBay 2 years ago. I ran some timing tests for the speed of running SVD. So this column, you can see this is in seconds very quickly. So here with a 10,000 by 10,000 matrix is just so slow. It's not something you really want to do. You really want to be doing in one way of address. This is so randomized SVD. So I also plotted something. Yeah. So in this plot here, I have plotted what the error is like. You can see here what the error is when reconstructing the matrix. And so actually maybe we can like discuss it about like drawing. Let me. So here we have got a matrix that you start with, and then you are decomposing it with U, S and V matrices. These may start with a large singular value 4.5, then 0.1 and 0.01 may not have that much information, so you can think of chopping it off, and correspondingly that will also mean that you are not gonna be using and chopping off, I guess, the last few columns of U. And then I am thinking about the matrix dimensions of line up that wider shape. So here in this graph, looking at the k is the number of singular values I get. So saying like if you throw away k, how close you reconstruct in your original matrix A. So here is these dotted lines here, you can see in the plot. So I refer to these two. So this is the PyBay talk, you can refer after the class, and this is computational linear algebra course, you can also refer this. The next thing I want to address is full versus reduced SVD. So using NumPy's SVD like np.linalg.svd vectors comma full matrices equals to false. So what difference make is this for traditional SVD, but the full SVD is going to have U and V both be square matrices, so that involves making up some columns. So oh, I didn't scroll it down. Okay, so that involves making up subcolumns. Here you can see these dotted things are actually columns, you can see. Okay, columns for you, so that don't directly depend on your data or whatever matrix should be composing, because you're also adding up some rows, pure zeros, or to your like singular values, which will be zero out with here. So we'll be using reduced SVD. It's quicker and to calculate, and you are often not needing to use to turn your like data into an orthonormal basis. Like, so it's been the meaning of that parameter. So that's it for today's class. So till then, take care. Bye bye.